The example we have is where incident light is just white light is shining on water. And you can see in the diagram there's a various range of colours. We're going to pick up the red colour, which has a wavelength of 636 nanometers. What is the minimum thickness for the film if we were going to see that red colour? So we set up our condition. We've got an oil on water. So the index of refraction for oil is 1.5, for water it's 1.3, and for air it's 1. Because the oil has a higher index of refraction than air, the wave reflecting off the top of the film is shifted by half a wavelength. So your delta A is half a wavelength. Because the water has a lower index of refraction than the oil, the wave reflecting off the bottom does not have this half wavelength shift, but it does travel that extra distance of 2t, thickness of the film. So the relative shift is therefore 2t minus lambda on 2. Now this is for constructive interference, so because it looks red, so for constructive interference, that delta also equals to m lambda. So in this case, 2t minus lambda on 2 is equal to m lambda. And if we move all the factors for the wavelength on one side and all the factors for t on the other side, we get 2t is equal to m plus a half times lambda. Now this actually looks kind of like the equation for destructive interference, but it's not, because we use the condition for constructive interference in step 4. It looks like destructive interference simply because you've got the m plus a half, but that's because of the phase shift in that first step. The wavelength in the equation is the wavelength in the thin film, so when we write it down, this must be obvious. We can do it in a couple of ways. We can put in lambda 2, or we can include the lambda vacuum divided by n2, and we can then solve the equation. In the picture that we are looking at, we wanted to look for the red film. This means that we need to choose the minimum value of m to find the minimum thickness of that film. So that would be just when m equals 0, which makes it a half of lambda in a vacuum over n2. So the T minimum is half of lambda over 4n2. So 636 divided by 4 times 1.5 will give you about 106 nanometers. So this is pretty small. We're talking 100 nanometer thickness, and that gives you completely constructive interference for the film. But if you use m equals 1 or m equals 2, then of course you're going to be doubling that thickness. So what about the other colours? So they're not completely cancelled out, because 106 is not the right thickness to completely destructive interference for any of the other wavelengths. The other colours do not reflect as intensely as red light, so the film looks red at that point. But we could do this same equation, but for blue light, which has a wavelength of 540 nanometers, and find out what would the thickness for the blue part of the film be. So let's look at destructive interference. This is the sort of interference that you might get for non-reflective coatings for lenses. So your glasses or your sunglasses or your camera lens or even your phones might have a non-reflective coating on it. And this generally has an index of refraction that's less than that of glass, so that both the reflected waves have a pi on 2 or 180 degree shift. The film thickness of about a quarter of a wavelength in the film results in destructive interference, which is derived in the expression below. So using the same diagram, but changing our coating to 1.36 instead of 1.5, and our glass to something a bit bigger, 1.5, instead of the water before, which was 1.3, we can have a look at it. So light reflecting from the bottom surface travels an extra distance of half a wavelength of green light. Green light is reflected from the top surface and interferes destructively with the green light from the bottom surface. So in other words, all the green light and most of the light in the middle of the visible spectrum is transmitted, but some of the red and violet light is reflected, so a coating would look a bit purple. How do we work this out? So in this case, you're looking at the index of refraction is between the other two indices of refraction. In your step-by-step approach, let's look at A, the first interface. So in the first interface, you've got n equals 1 and n equals 1.38, so you're going to have a pi on 2 shift. In the second interface between 1.38 and 1.52, you're going to have another pi on 2 shift. So that's in addition to the thickness of the film. So delta A is equal to lambda on 2, and delta B is equal to 2t plus lambda on 2. So the overall change is 2t is equal to, well, because you've got delta b minus delta a, so you eliminate this lambda on 2. So the overall change is just 2t. That means that your 2t for destructive interference is going to be equal to m plus a half times lambda of the coating. So your minimum is again going to be lambda of the coating divided by 4, and not forgetting to include the refractive index of the coating when you're trying to compare it with the wavelength in air or in a vacuum. So just to show you some of the diagrams that we might get, this is from physics at UNSW. They have a lot of animations on there, and this is a diagram that shows you the waves as they were travelling in, and that condition for the thin film lambda on 4n. If we actually look down here, you can see some of the diagram, the non-reflective coatings, and you can see that they do actually appear, well, blue-violet, I think they call it. The lens in the photo above appears to have a blue-violet tinge, which is a simple way of recognizing these coatings. So if we actually look at the animation, you can see that the wave comes in and is reflected off the top one with a phase change and reflected off the bottom one with a phase change. So you get complete destructive interference. So we can use these conditions for constructive and destructive interference in thin films. In nature, we can observe them in things like butterflies. So this is an example of a morpho butterfly, which has particular ridges and scales on its wings, which cause this interference condition to occur. So you can see the dark spots are the destructive interference, and the light spots are the constructive interference. And the constructive interference for this particular butterfly is blue. And I'm sure you've seen the monarch butterflies, which are bright orange, and various other ones. But this one is blue, which means that your lambda on 4n for the thickness is going to be around about that, so that you can get a lovely blue image out. So why is it that the wavelength in the film really matters and not the wavelength in air? It's a bit hard to see from the animations because they're moving, but in a diagram you can see it quite easily. So in figure A we have our wave incident on a surface, and the film here is just the right thickness to be half the wavelength of the wave when it's in the film. So that wave comes in and just manages to reach the end. And then figure B shows the situation 2 periods later. So the wave comes in and then it has to travel back out and again. Part of the wave initially was reflected, but remember when it gets reflected, it's reflected with a phase transition. So you can see the one that's reflected with the phase transition is now going to interfere destructively with the one that has now come out from the bottom of the surface, so from that second interface. Figure B shows the situation 2 periods later, after 2 complete wavelengths have encountered the film. Part of the wave is reflected off the top surface of the film, and this reflected wave is flipped by 180 degrees, so the peaks are now troughs and the troughs are now peaks. This is because the wave is reflecting off a higher index medium. Another part of the wave reflects off the bottom surface of the film, and this does not flip the wave because the reflection is from a lower index of refraction medium. When this wave re-emerges from the first medium, it destructively interferes with the wave that reflects off the top surface, and this occurs because the film thickness is exactly half the wavelength of the wave in the film. Because a half wavelength fits in the film, the peaks of one reflective wave line precisely up with the troughs of the other, so the waves cancel. Destructive interference would also occur with the film thickness being equal to one wavelength of the film, or 1.5 or 2, so any of those conditions. And if the thickness was a quarter, or 3/4, or 5/4, then the wavelength in the film would have constructive interference. This is only true when one of the reflective waves experiences a half wavelength shift because of the relative sizes of the refractive index. If neither wave or both waves experiences a 180-degree shift, there will be constructive interference when the film thickness is a half, 1, 1.5, 2, and destructive if the film is a quarter, 3/4, 5/4. So that phase shift really is important, as that's why it's the first step in our problem solving. Something you might want to think about is, in the diagram above, we drew 2 reflective waves and we say they cancel out. But this means that none of the wave is reflected out of the medium. Where does it go? It must all be transmitted into the third medium. I mean, that's the whole point of having a non-reflective coating, is to transmit as much light as possible through a lens. So even though we did the analysis by drawing the waves reflecting back, in some sense they don't really reflect at all because the light ends up in medium 3.